You know, when you look at something massive like the Eiffel Tower or the Golden Gate Bridge, you ever stop to think what's holding it all together? It's millions, literally millions, of these little steel pins called rivets. But that kind of begs the question, right? Why use so many tiny parts and not just, giant nails? Yeah, it sounds like a simple question, doesn't it? But the answer is so much cooler than you'd think. It's not about finding a stronger pin at all. Turns out the real answer is all about fighting an invisible enemy. Okay, so to get what this enemy is, picture a thick deck of cards. If you bend the whole deck, what happens? The cards all slide past each other, right? Well, that is exactly what's happening inside a huge steel beam when it's under load. All its internal layers are constantly trying to slip and slide and shear apart from each other. And that force, it actually has a name. It's called shear flow. And it is a powerful, relentless force that's always trying to tear a structure apart from the inside out. So yeah, for our story, this is absolutely the villain. So let's go back to our giant nail idea. I mean, it seems logical, right? But here's the thing. A nail works great in wood because the wood fibers literally swell up and grip it super tight. But in smooth, hard steel, that same nail would allow for these tiny, disastrous little slips. And that's a huge problem. And that right there is the fundamental mismatch. Wooden nails, that's a dynamic system. It can bend and give a little. But a massive steel structure, like a bridge, it demands absolute, total rigidity. There is zero room for error. Any slip, no matter how tiny, could lead to catastrophic failure. So a nail just wasn't going to cut it. They needed a completely different way of thinking. And this is where the real genius kicks in. The engineers had this brilliant realization. The solution wasn't to find a stronger pin to block the force. No, the solution was to create a whole new, powerful force of their own. So they came up with the hot riveting process. On the surface, it's pretty simple. You heat a rivet until it's white hot, you stick it in the hole, and you hammer a second head on it. But the real magic, the real physics happens when it starts to cool down. As that metal shrinks, it contracts with this incredible, immense force. And that creates the powerful clamp we've been talking about. Okay, so get ready because this is the part that changes everything. This is the big reveal. A rivet's real job, it isn't to block that shear force at all. No, its job is to use that incredible clamping force from cooling down to squeeze the steel plates together so tightly that friction can stop it. That's the hero. Not the rivet itself, but the friction the rivet creates. The grip between the plates becomes so unbelievably strong that it just stops that shear flow dead in its tracks. The plates can't slide. It's genius. Let's just break this down real quick. A nail, right? It has to physically take the hit. The shear force pushes directly on the body of the nail. But a rivet, it plays a totally different game. Its job is to create so much clamping power that the plates themselves lock together with friction. They act like one single solid piece of steel. The amazing part is the rivet itself barely feels any of that shear stress. It's just there to squeeze. And this incredible counterintuitive principle, using clamping force to create friction and using friction to create unbreakable strength, this is the secret that literally built our modern world. It's behind some of the most massive, iconic structures you can possibly imagine. I mean, just think about the scale here. The Titanic. 3 million rivets. 3 million of these little clamps, each one creating its own little zone of insane friction, holding that whole hull together against the absolutely crushing pressure of the North Atlantic. It's mind-boggling. Or how about this one, the Sydney Harbor Bridge? We're talking 6 million rivets, 6 million individual clamps, all working together to lock that bridge into one single, unmovable, unbreakable arc against the sky. So let me ask you this again. What is a bridge? Is it millions of simple pins holding steel together? Or is it millions of tiny, incredibly powerful springs constantly squeezing, turning separate pieces of steel into one single, unbreakable structure? The next time you see one of these engineering marvels, you'll know the answer.